and what you call dt. Okay, so this is what you can do. So by choosing q equal to this and taking the both sides power q of this inequality and integrating from 0 to infinity, you're going to reach this. And let's simplify this mess. So what are you going to get? So you're going to have a c times 0 to infinity. So you have the gradient of u squared times in h norm times h norm of p square by p minus 2 and dt. Okay, p square by p minus 2 and dt. Okay. Now what I want to do is that I want to estimate this side by a constant. Okay, by a fixed constant. Now what I can do, okay, so I can explicitly write that, okay, the things inside the norm depend on the time t. So what I can do is that, for example, if I take this on, if I pull this, I take the supremum of the u of t h norm and pull this out of the integral, so you're going to get, what do you call, this is less than or equal to c times of the supremum t from 0 to infinity and u of t e square by p minus 2 and 0 to infinity, the gradient of u of t square, what do you call, dt. Okay, this is what that you're going to get. Now if I call all of this as, say, a constant k1, okay, that depends on obviously u naught and f, and I call this stuff as a constant k2, that obviously depends on u naught and f and mu, okay, then I can say that this is less than or equal to c times of u less than or equal to k1 power, okay, so k1 power p square minus p minus 2, because the norm of u of t is less than or equal to k1 for all t. So so the supremum would also be less than or equal to this, and for this I know that this is less than or equal to, what do you call, k2. Okay, and I can call all of these things again a constant c. Okay, a constant c. So that depends on u naught, that depends on f, and that depends on, what do you call this, kinetic viscosity, mu actually. So it depends on these three things. So what does this mean? What does this mean? What does this show actually? So this shows, I will refer to a result. So I will refer to a result, theorem 0.1 in the paper that I mentioned, Vira 87. We can deduce that this LP norm of UT is uniformly bounded. UT norm of LP is uniformly bounded by a constant phi that we have already talked about, that depends on u naught and depends on f and depends on what do you call this 0 to infinity u norm of what do you call LP power q dt. Okay. So we can show that this is uniformly bounded by a constant that depends on u naught, f, and what do you call the estimate that we have made actually. So I'm relying on the result of the beta in 87 actually. Okay, so I'm not gonna. So what you have to do is just read out the theorem 0.1 and make sure you understand that why using theorem 0.1 and obviously n being 2 dimension and this estimate, you can have what you call the uniform boundedness of LP norm actually. Okay, and once you have the uniform boundedness of LP norm for all t in the interval 0 to infinity, your solution is continuous and valid on the entire timeline 0 to infinity, and hence your solution is global. Hence U is global solution actually. Okay. All right. So what does this show? That our 2D Navier-Stokes equation and the certain assumptions has a global solution actually. Okay, in the respective space. So what is the key thing that next we would like to do? The thing that I'm interested in, basically, mainly doing, mainly for that I'm interested in doing in this result actually. Okay, so we talked about existence uniqueness in our last discussion. Okay, and there is a huge literature on variety of versions of Navier-Stokes equation actually, and discussing their existence, uniqueness, and different kind of properties. But what I would like to show now, I would like to give to you what you call this lemma. I mean, we proved this lemma in our lecture 1 in this series of discussion, and we proved a different version of it actually. But here I want to talk about a stronger version of the same lemma actually, in which you have some weaker assumptions. So, and this lemma allows you to study the long-term behavior of some kind of evolution equations actually. So let's recall what was it. So suppose y of t and h of t are such that they are both continuous and non-negative. So y of t and h of t, y and h are continuous and non-negative, and they satisfy what you call rather an integral inequality. I mean, if you remember, previously we had a differential inequality actually. But now if we what do you call simplify or replace that differential inequality by rather a weaker condition, which is this integral inequality. In other words, your y satisfies this, and obviously your y and h both are integrable, okay, over the entire interval 0 to infinity. Then if y of t would go to 0 as t goes to infinity. Okay, so here to study what you call the long-term behavior of the LP norm of the solution of the global solution of the 2D Navier-Stokes equation, I'm going to use this lemma. Okay, so what I have to show? I have to show this, and obviously I have to show this, but first we need to make sure that what comes as h, and I have to show that my y satisfies this inequality. So this is what the key thing is. Okay. So let's move on and apply this lemma. So what is our next task? So next claim is that if you take your global solution for 2D Navier-Stokes equation and you take y of t to be, say, the LP norm of the solution with the power alpha, okay, and the alpha is what do you call this, p square. Alpha is p square by p minus 2. Then your y satisfies the both conditions of the lemma. In other words, this condition, and this condition. Okay, it satisfies these two conditions, and when it satisfies these two conditions, then we will deduce that y of t goes to 0 as t goes to infinity. So our task would be to show this and these two conditions are satisfied for y. Okay. By the way, we can give these both conditions a name actually. So let's call this condition as condition star and call this condition as condition double star. Okay. Since you have uniform boundedness in LP norm, so it's not difficult to show the condition, what do you call, double star to prove actually in the lemma. Okay, so that's what then y satisfies star and double star, and hence y of t goes to 0 as t goes to infinity. This is what that I am interested in showing actually. Okay. As I said, condition 2 is not that difficult to show. Okay. So let's start with, say, condition double star. Okay. So what do we need to do? I need to integrate from 0 to infinity this y of t dt. And then y of t dt is 0 to t infinity u of t LP norm of alpha and beta. Okay, this is what it is. So I have this fact that the LP norm raised to q and its integral from 0 to infinity is bounded by a constant actually. So I want to exploit this fact actually. So here's the thing that I can do. So let's do this. So let's break this down into two powers. So say u of t LP and say call it q times u of t LP norm of alpha minus q dt. I can take supremum over the time and pull this, what you call, object out of integral. So let's take that. I can have a supremum from t equal to 0 to infinity of u of t LP norm of, what do you call, raised to q, okay? And what is going to remain inside is 0 to t u of t LP norm of, no, this should be alpha minus q, and this should be q and dt. Okay? And we have to keep in view that q is this 2p by q minus 2. Now for this, I know that this guy is less than or equal to a constant. We called it C, that depends on u naught and f and mu. U naught, f and mu. Okay, this is what it is. And how can I show that this is also bounded? You know, what can I do? That I can apply my Gagliardo-Nierenberg inequality actually. Okay, so by the Gagliardo-Nierenberg inequality, this can be estimated by, what do you call, supremum of the gradient of u of t, okay, supremum of the gradient of u of t, but okay, I don't need to apply gradient inequality, but since I know that my u of t is uniformly bounded in this space C 0 to infinity LP, so this should be also bounded by this definition actually. So what would be the norm on C 0 to infinity LP? So it's going to be supremum norm, okay, with LP. So for sure this is also finite. So I can say that entirely that all of this, you know, this 0 to infinity y of t dt is less than or equal to a constant actually, a fixed constant C. Okay. That depends on u naught and f in initial condition actually. Okay. So since we had global solution here, okay, so maybe some people use global, and as I mentioned in the beginning of this discussion that lives in this space, so using this norm it is not difficult to see that this must also be finite actually. Okay, because the supremum of u of t LP is finite, so its power alpha minus q is also going to be finite. So this is finite, this is less than or equal to the constant, so this entire side is less than or equal to a constant, and this is what the precisely condition double star for y of t was. The key challenging thing, okay, that you have to do and we have to do is to basically show the star condition, okay, that this condition, the integral inequality, that y of t minus y of s can be less than or equal to some function that depends on y of t plus some independent function h of t, which is non-negative and continuous actually. So if you have this, then by lemma our y of t goes to 0 as t goes to infinity. So this is what that I would like to show. Okay. So now let's move to the proof of a star for y of t. Okay. By the way, there are some calculations that I'm going to do, and there are some calculations which I'm just orally going to tell you and you have to do for themselves. And there are some calculations for which I'm going to refer to this paper by the Bira in 87 again and again actually. Okay. So the trick to show this inequality is going to be that first I'm going to show that this inequality is true for, you know, what you call the approximate solution. Okay? So in other words, such an inequality is true for the approximation of the U actually. Okay? So if U is the solution of the Navier-Stokes equation, then, you know, we can have a sequence, okay, that I'm going to write in an appropriate space that approximate it actually. And if the star is true for that approximate solution, okay, and we have good estimates, then I can take the limit and the inequality will be proved actually. Okay? I know it's like waving the hands, but you know, I'm going to do step by step, so don't worry. So suppose I have a sequence U naught k and Fk such that, okay, or Uk naught, such that Uk naught approximates U naught in LP intersection L2, okay, and Fk approximates F strongly in L1 over the interval 0 to infinity with LP intersection L2, and Fk approximates F in weak star sense okay, sense in L infinity 0 to infinity with LP. Okay. All right. So in other words, in your Navier-Stokes equation, replace Uk naught by U naught and Fk by F actually, or F by Fk. Okay, where Uk naught and Fk, I know about U naught that it sits here, and I know about F that it sits in these two spaces. So I can find such sequences that approximates F actually. So what I need to do, I need to take my Navier-Stokes equation and take take the condition. So take the Navier-Stokes equation and take the initial condition as Uk naught, and take the forcing factor as Fk instead of F, Uk naught instead of U. Then we know by the previous analysis that there exists a unique solution for such problem actually. So in dimension 2, by the way, you can also assume about Uk naught and Fk that they have the compact support actually. Okay, they also have compact support. They are continuous functions with a compact support. So then for each Uk naught and Fk, there exists a unique global solution to our original Navier-Stokes equation. Okay, and let's call that global solution as Uk. Okay, as Uk. That is UK naught and FK satisfy this. So UK naught partial by partial P minus Laplace UK plus UK dot del operator operated onto UK plus gradient of P equal to F actually. Fk, okay? Pressure is not changing, so it stays the same. And obviously divergence of UK is 0 and UK of 0x is UK naught of x. Okay, so this is what I'm saying, that okay, for UK naught and FK there exists a unique solution actually. Alright. By the way, I must say here that these UK naughts are also divergence free actually. Okay, so they are divergence free. So initial conditions are divergence free. So whatever the assumptions we had previously on U naught, you also have on UK naught actually. Okay, so what I need to do next, take this equation. I'm writing it explicitly for a purpose. Take this equation, multiply this for by the way, I must say that what I would like to do, so where we are heading, so what I would like to do is that first I would like to show my star inequality for yk of t, that is LP norm of UK of t power alpha. Okay, so for this I would like to show that my inequality is satisfied actually. Okay, and all this stuff that we are doing is to show this, and then I would like to show that if I'll take the limit k goes to infinity, my original u would satisfy, or my original y will satisfy the required inequality star actually. Okay, so that's what is the key thing that I would like to do and I'm heading for. So multiply this above equation for with UK power p minus 2 UK and integrate. Okay, and integrate with respect to x. That is what I would like to show is that take your partial u by partial t, UK by partial t, and take UK power p minus 2 UK and take this inner product in L2 in H plus minus mu Laplace UK plus UK dot del UK operated onto UK, and it's in a product with UK power p minus 2 UK, okay, plus gradient of p UK